So now, I'm really pleased to welcome Valérie MASSON-DELMOTTE. It's really a privilege and a pleasure to welcome you today for this opening conference. You are Research Director at the French Alternative Energies and Atomic Energy Commission, CEA, at Pierre-Simon Laplace Institute at Paris-Saclay University. Your research team is interested in the study of climate and the hydrological cycles through the analysis of stable isotopes of water and air molecules. This involves understanding past and current climate variability to better characterize the coupling between climate and the atmospheric water cycle. You have served on numerous national and international projects, including the Intergovernmental Panel on Climate Change, and you were associated with the Nobel Peace Prize 2007, awarded to Al Gore and the IPCC. From 2015 to 2023, you have been elected co-chair of the Working Group 1, the physical science basis of the IPCC, which contributes of understanding of how the climate system works and how it is changing in response to human activity. You have published major publications, including several books for the general public, as well as children's books, and you receive a number of prizes and medals for your extensive scientific work. So we're really pleased to welcome you. Come by, and the floor is yours, and you're going to give a conference on climate change and transformation challenges.
Thank you very much. Thank you very much for this invitation to come here and share the state of knowledge regarding these transformation challenges. It's a pleasure to be here in Reims, and it's also a pleasure to see numerous colleagues, as well as young, bright minds, and we need you to tackle these challenges. This is one of the figures from the last IPCC report released last year, the synthesis report. You can see 1 year, one stripe, and an indicator of the state of climate, changes in global surface temperature. So we're reaching a level of warming during the last decade of 1.2 degrees Celsius now, at an intensifying pace compared to the pre-industrial period. And why do I speak about transformational challenges? You can see the outcomes of future climate assessments in response to 5 very contrasted scenarios: very high or high greenhouse gas emissions in the future, the intermediate scenario, which is closest to public policies in place now in the world, and in the case with much more effective climate action to reduce greenhouse gas emissions fast or very fast. In any case, global warming will continue until global carbon dioxide emissions reach zero net. First transformation: build on scientific knowledge to anticipate future changes in climate, prepare for it, manage risks, and implement adaptation responses in each region, in each sector. Second challenge, and we'll see that some of the risks will be very hard to manage. There will be limits to adaptation for ecosystems we depend on, for water, for biomass, for critical aspects, including health. So the second transformation challenge is to reduce emissions as fast as possible. I'll show that there are options available to do it, but there's also a huge need for research, development, innovation, so as to be prepared to decarbonize hard-to-abate sectors. And we have added people of different ages. We could also add other forms of lives, coral reefs, trees, long-living mammals, because what matters are the living conditions for us, the old ages of those from my age, or the conditions for the youngest ones during the coming decades and centuries. So, just a word about the scientific basis for this presentation. It is grounded in IPCC reports, 3 special reports released in 2018, 2019, 3 main reports released in 2021, 2022. A special report, 500 pages. A main working group report, 3,000 pages. There are 100-page summaries and 20-page summary for policymakers. These reports are grounded in the assessment of evidence from scientific, technical, socio-economic publications. Each chapter is reviewed several times, and the summary for policymakers is part of a co-production process. At the beginning, we listen to the needs expressed by all governments. They are part of the process. They nominate scientists to read, to review the reports. And at the end, they scrutinize word by word the summary for policymakers. There's no equivalent in terms of a scientific peer review process at depth, so that the assessments are transparent, rigorous, the conclusions reflect in a balanced way and clearly what is underlying this. And this approval process makes this report a scientific basis recognized by all parties. So it allows to separate the scientific evidence from climate negotiations that can be grounded on this common basis. If you don't like to read long reports, there's a French company that has developed an artificial intelligence tool in the spirit of ChatGPT so that you can navigate across the reports and you can formulate a plain language question and see where the various parts of the reports related to your question. And I think this is powerful for you to be able to navigate in the reports for the topics you are interested in. I'm also part of the National Climate Change Committee, which is different. IPCC looks at the global picture, does not look at the policy of a given country, does not make any recommendation. It has to be neutral. So for all possible solutions, it looks at the potential, limits, costs, co-benefits or trade-offs, but it does not make any recommendation. And this can be frustrating, to be honest. So within the National Climate Change Committee, it's different. We look at French climate ambition, we look at the targets, we look at the implementation of climate policies, what works, what does not work, and we develop recommendations. And I think, for me, it reflects what is expected from scientists. Not just new knowledge, knowledge that is relevant to inform decision-making, a role of trigger of climate policies, and sometimes, in challenging contexts, a role of watchdogs so that the preservation of a healthy planet is implemented and supported by climate policies. So let's dive into where we are now in terms of the state of climate. I'll focus on the global picture with a few highlights for France. So we are in a context where climate action is gaining momentum. In France, as in around 20 countries, greenhouse gas emissions are decreasing, including consideration of imports. We see that more than half of greenhouse gas emissions are in the scope of public policies, which have prevented the emission of several billions of tons of greenhouse gases, in particular through policies of technological innovation and efficiency. It's also the case for public policies targeting deforestation. We also have progresses in adaptation strategies and planning, but often reactive. You are hit by a heat wave, you prepare for the same type of heat wave. You're hit by a drought, you prepare for the same time of drought. But it's not enough transformative. It does not prepare you for the new unprecedented events that will occur in the coming decades in a warmer world. And there are insufficient financial flows. So the pace and scale of what has been achieved so far globally is not sufficient to limit the escalation of climate-related risks. This is illustrated here when we look at global greenhouse gas emissions. They are expressed in the equivalent of carbon dioxide over 100 years. This is the metrics used here. You can see that global greenhouse gas emissions are dominated by carbon dioxide, 90% of that due to fossil fuels, coal, oil, and fossil gas. You can also see that 10% of CO2 emissions are driven by land use changes, in particular deforestation, destruction of peatlands. And for other greenhouse gases, the second most important one is methane, a third of it due to leaks from fossil fuels, a large part of it due to agricultural practices, in particular livestock and meat consumption. So what you also see is the increase in global greenhouse gas emissions, but for CO2 at a slower pace in the last 10 years. You have the effect of the COVID-19 pandemic and the rebound. However, the latest estimate for 2023 still shows a global increase in CO2 emissions from fossil fuels. We are not yet at a stage where we have managed to reach a peak and a clear decline. And that illustrates also the urgency. So what is driving this? Unsustainable use of non-renewable resources, fossil energy, unsustainable use of land, lifestyles, patterns of consumption and production that are not sustainable across regions, between countries. So there's, of course, a larger responsibility of those who have industrialized first, and now emissions are being increasing by large emergent economies. There are huge contrasts between per capita emissions between countries. They are very small today in India or Africa per capita. And finally, there are huge contrasts between individuals. 10% of people in the world account for 40% of emissions, while half of the world's population only accounts for 15% of greenhouse gas emissions. And this half of the world's population often lives in very vulnerable contexts. This illustrates challenges of climate justice and equity. So we add greenhouse gases, their levels are increasing in the atmosphere. Today's level of CO2 is unprecedented in more than 3 million years. The level of methane is 2.5, the pre-industrial level. This is completely unprecedented in terms of magnitude of the rise of concentration and speed. This traps energy, which cannot escape to space, and the climate system is reacting to this perturbation with amplifying factors: warmer atmosphere, more water vapor in the atmosphere, more greenhouse effect from the water vapor, a warming effect from clouds, the loss of snow and ice, losing the mirror effect, amplifying surface warming. So where does the excess heat go? The excess heat trapped in the climate system. 1% warms the atmosphere, 5% warms the soils. Of course, it affects every form of life over the continents, the growing season lengths, for instance. 3% is converted into the melt of snow and ice. 1 kilogram of CO2, 15 kilograms of glacier ice to be lost. 1 degree of global warming, 1 month less of snowfall in mid-elevation in the Alps. These are two direct illustrations. So a widespread loss of glaciers. The melting of Greenland has increased. The fast flow of some Antarctic sectors has accelerated. And so ice stored on the continents reaches the ocean and contributes to sea level rise. Most of the excess heat goes into the ocean, 90%. It makes the ocean expand. The rate of sea level rise is accelerating as a direct consequence of the perturbation of the Earth's energy balance. And there are irreversible aspects. The time span for mixing of the ocean waters is several hundreds of years. The ocean is picking up heat, carbon leading to its acidification, deep ocean changes, sea level rise, they will be irreversible on hundreds to thousands of years. And that's what we are triggering now. So if we look at global warming, the figure I showed previously with the stripes, this is the assessments that we had in 2021. And you can see that the red bar show observed warming. The second red bar show what is due to human activities. And you can see that it is equal to observed warming. The effect of greenhouse gases, the first gray bar, is larger than what is observed because it's partly masked by the cooling effect of pollution particles. And in the last 20 years, due to air quality improvement policies in Europe, North America and China, there have been targeted policies to remove the emission of these particles. Of course, that's beneficial for public health, but we have lost the cooling effect of the pollution particles. It adds to the warming effect of greenhouse gases. Now these two factors go in the same direction. So we have implemented a process from scientists who have developed the IPCC assessments to provide an annual update to the state of global climate. So the first one was released in June 2023. You have the list to the publication. What does it show? 2 years from the last physical science basis assessment, an increase in greenhouse gas emissions, an increase in concentrations in the atmosphere, more heat trapping effect, more warming due to human influence. What also I would like to highlight is the state of global climate updated until the end of 2023. You can see record warming at the global scale. We are close for the first time to reach 1.5 degrees Celsius above pre-industrial. It has occurred at the scale of a few months. It's the first time it's occurring at the scale of 12 years. And the more you add greenhouse gases, the more frequent it will be. When it's 1 year out of 2, expected by 2030, it means we've reached that level of warming, not just for 1 year, but in the climate sense, averaged over 20 years. And a surprise recently was the loss of Antarctic sea ice. You can see that until 2015, there were large fluctuations, a small increasing trend, but now we see years with extreme loss of Antarctic sea ice. It could be caused by the uptake of heat by the ocean around Antarctica, preventing sea ice to form, in the case of storms that dislocate it. And so maybe a new state encountered in this region. It illustrates that what happens over the continents affects the whole planet. And if we want to preserve pristine ecosystems around the Antarctic, we need to limit the magnitude of warming. Warming affects mean climate everywhere. It also affects extreme events. A direct consequence of a warmer climate is a reduced frequency and intensity of cold extremes, and an increase in the occurrence and intensity of hot extremes. One hexagon is a world region. We are here in Western Central Europe. South of France is in the Mediterranean region. And every region in red is where we observe this intensification of hot extremes. The number of dots indicates the confidence in the attribution of the likelihood of occurrence and intensity to human-caused climate change. It's widespread. In 2019 in France, more than 45 degrees in the south of France, this type of event would have been extremely unlikely in a pre-industrial climate. For rainfall, it is a direct effect of a warmer atmosphere, which can hold 7% more moisture per degree of warming. The same storm today can lead to much larger amounts of rainfall compared to a few decades ago. This is already observed in the south of France. It starts to be observed for thunderstorm events in these latitudes, an increase in the record intensity of thunderstorms. And our infrastructures water systems are not designed for these extreme rainfall events. We have also artificialized a lot of soils through urbanization or agricultural practices. So both local features and climate change combine to increase flash flood risks in many regions. And finally, a warmer atmosphere leads to more evaporation, more transpiration, an increase in what we call the atmospheric demand. Therefore, it transforms a normal period of reduced rainfall in a more severe drought. So the regions that appear in yellow are regions where we see an increase in the frequency and intensity of these agricultural droughts that affect soil moisture. Drought and rain and heat combine to increase water and heat stress on plants, animals. They can combine to increase the occurrence of fire weather conditions that can lead to more extreme wildfires. This is observed at the very large scale and is also a result of warming. Coming back to impacts and risks, they are not just the outcomes of these hazards and these climatic impact drivers. They are the result of their interactions with exposure, vulnerability, and the responses that we can implement to limit impacts and risks. This is what I presented previously without the data. These are emissions per person in more than 180 nations. You can see in some places of the world, like Qatar or Emirates, like here, emissions that can be more than 20 and up to 40 tons of CO2 per person and per year. In North America, Australia, more than 15 tons per person and per year. In Europe, it's usually around 5 to 10, depending on the energy mix. However, half of the world's population has emitted almost nothing in the past and today, and lives in countries with very high vulnerability index to a warming climate. And that's the illustration of climate justice, where you have those most responsible and those most vulnerable who need to discuss together on what is the best strategy to tackle a changing climate. In these most vulnerable contexts, there's a need for basic access to public services, water, energy, education, health. So the challenge is to find affordable solutions that can make low-carbon solutions available for those who have the most urgent need to access these basic services for development and for the quality of life. If you are interested to follow up, what is the diagnosis we can have on high-impact events? I give you two sites here. One is the World Weather Attribution Project. It's a group of scientists that looks at high-impact events and answer the question, is it just a rare natural event, part of climate variability? Can we see the fingerprint of human-caused climate change? How do our models represent what is observed? And how much will these events that have already high impacts will continue to recur and intensify in the future? And you can see examples of recent outcomes. For instance, footprint of human-caused climate change on wildfires in Canada last summer, leading to the emissions of 500 megatons of carbon due to the loss of carbon stored in Canadian forests. This illustrates some of the feedbacks that can be triggered in a warmer world if the biomass storing carbon is lost and that carbon goes back to the atmosphere. Today, the vegetation and soils absorb about a third of our CO2 emission. The ocean, about 25%. This is a giant service provided by ecosystem, picking up about half of our emissions. But in a warmer world, the efficiency of these sinks will be challenged by a warmer ocean mixing less well, and by the effect of heat, water, fire stress on vegetation and soils. So what we see now is the increase of widespread impacts and losses and damages attributed to human-caused climate change. And you know, we are living in Europe in an agricultural crisis. Food production is at the forefront of climate impacts. They affect physical renewable water availability, crop production for agriculture and livestock. They affect the production of aquaculture and fisheries. The fish catch potential in the tropics has reduced due to a warmer ocean. There are multiple effects for health, in particular excess mortality associated with heat waves, but also mental health due to displacements, in particular people affected by floods and affected by wildfires that have to move from their homes are affected by mental health trauma that can persist for months. For cities, the largest impacts are associated with flood risks. In France, we are particular because we have 10,000 houses built on argillaceous soils that are affected by swelling and shrinking in the case of droughts. So we are particularly exposed to building drought risks with increased insurance costs. And half of the studied species are moving just to try to keep their habitats. We see mass mortality of species over land and in the ocean. Tree mortality in France has strongly increased just in the last 10 years. And the ability of the growth of forests to store carbon in France was around 7% of our emissions 1 decade ago. It has decreased to only 4% now. So it illustrates the loss of services from these ecosystems, including carbon storage. I've added a few pictograms just to give highlights. The habitat suitability for some vectors of diseases, such as ticks, mosquitoes, or midges, is expanding. Today, livestock farming in France is affected by a new disease, epizootic hemorrhagic fever, transmitted by midges, biting midges. It is shown that the habitat suitable for this midget is reaching Europe due to warmer conditions and milder winter in particular. The mosquito is to illustrate the increased risk for dengue fever. We see now a widespread outbreak in the tropics of dengue fever. The vector-borne disease is now installed almost everywhere in France, tiger mosquito. And we have now autonomous cases with an increased risk and an additional pressure on the health system due to these effects. So just to remember, these impacts, they are caused by changes in physical climate conditions attributed to human influence on climate, and they will increase with every increment of future warming. As students, what can you do? You can learn how to access to this information, climate data, climate projections, to learn to use the 33 climatic impact drivers that have been identified, and do stress tests for future projects so that for a city, for an industry, for an agricultural activity, you are able to provide a climate service that allows to better prepare, manage risks, and adapt. Just coming back to France, we're strongly exposed to climate change, including for food production and not ready. This was illustrated in 2022 with a cost for insurance companies of 3 billion euros, and these are only the insured costs. 2022, 3 major heat waves, major wildfires, including loss of wetland species, marine heat waves, and multiple consequences of drought, including shortage of drinking water provided to several municipalities. 2023 has been the second hottest day. So you can see in France, for 1.2 degrees globally, we are already at 2 degrees for the last decade. These record years are reaching 3 degrees above pre-industrial. So we are entering into new territory. We had again an exceptional heat wave last summer with an excess mortality of more than 5,000 people. The hottest fall on record. Well, today is a record, actually, in February. And we had record monthly precipitation, including major floods and impacts in northern France, together with severe drought in the south, and in overseas territories, record heat and historical drought, including affecting dramatically water resources in the island of Mayotte. Thinking of losses and damages, there has been an advance recently at COP28 with a new fund in the spirit of climate justice to help those most vulnerable, most affected to recover and rebuild after disasters. Just to give you a hint of where we are in terms of challenges, countries have given pledges to contribute to that fund. France is playing good, about $100 million on the table. US, first historical emitter, one of the largest emissions per capita, exports of fossil fuels. They have only placed on the table $17 million. It's honestly ridiculous. And it illustrates how much those responsible for emissions are extremely reluctant to be accountable for the loss and damages that they cause. Profits of fossil fuel companies, they don't contribute at all to the loss and damage costs. This illustrates some of the challenges that we see. And to give you a sense, what is on the table is around $0.7 billion on this new fund. The costs to address losses and damages, they are expected to be between 100 and 400 billion. What has been put on the table is only equal to the salaries of the 3 most well-paid football players in the world. Are we serious? So let's look at the possible futures. And the possible futures, they depend on us. The geophysical knowledge has advanced. The climate response, constrained by what we know from past climates, feedback loops, observational constraints, it has allowed to reduce the uncertainty on this climate response by a factor of 2, but we need to continue to advance that. This is only shown by 2050, because if warming is really large, more than 2 degrees after 2050, then we enter more uncertainty about the carbon cycle feedbacks that could increase the uncertainty on this relationship. However, this is a very solid geophysical constraint showing the close link between cumulative CO2 emissions and warming. In black, you have what has already been observed, and then you have projections for different future scenarios. What does it say? It says every ton of CO2 we add contributes to future warming. What we also know is that if we would put our CO2 emissions to 0, okay, now or through transformations to be implemented, there would be no more warming. There's an uncertainty by a few tenths of degrees, including on the sign. So the second thing is, we need to reach net zero CO2 emissions if we want to limit future global warming. And when we reach that, we expect warming to stabilize. That will be the dominant effect and the dominant player for future warming. Of course, we also need to limit the net effect of other greenhouse gases and particles. But if we don't act on CO2, we won't stabilize future warming. That's the key thing. So it's the same graph as the stripes at the beginning, but it illustrates the scenarios of emissions on the left side panel, very high, high, intermediate, low, and very low emissions. And then it illustrates the temperature response at the global scale. So maybe the positive thing is the following. If we strongly reduce emissions at the global scale, we would see the benefits within 20 years of global warming stabilization. The second thing is, reality won't look like these boring curves. What is shown here is the average of all climate models constrained by our assessed climate response. In reality, you'll have volcanic eruptions, you'll have natural variability that will modulate these trends. A few years ago, they played in the opposite direction as human-caused warming, with the appearance of a slowdown. Warming had continued, but for surface temperature, it showed a slowdown. And some people jumped on it. Warming has stopped, no need to worry. At the moment, it's playing in the same direction. So we see very fast warming, extreme year 2023, because we have an El Niño on top of human-caused warming. Some people think it's out of control. We can't do anything anymore. So it also requires to be able to discernate the gradual human-caused warming effect from these modulations by natural variability and not over-interpret single years. I'm a paleoclimatologist. It's always useful to place current changes in a broader context. So here you have 60 million years, the past 1,000 million years, and the last 2,000 years. What you can see in the upper panel are changes in atmospheric CO2 concentration, and you can see how fast we've been out of the range of the last billion years, recreating an atmosphere that was previously similar 3 to 14 million years ago. On the lower panel, you can see estimates of past changes in global surface temperature. Warming observed to date. Now we are out of the range of the current interglacial period when we look at the last decade. And future warming projections. Limiting warming close to 1.5 degrees, it means staying in the range of the warming of the last interglacial periods. More than that, it's unknown territory. It's unknown territory for many ecosystems, not just because of the mean warming, but also the pace, which is tens to hundreds of times faster than those of the past, in particular in the tropics. What can we learn from the past? There are still a lot of things to learn. Acclimatization of species and ecosystems, organisms, but also limits to adaptation capacities. And we do not fully take use of what we can learn from the past. What does every increment of warming mean? The more you have warming at the global scale, the more you have warming everywhere, with a larger warming overland and very large around the North Pole. When you increase the warming level, you intensify the water cycle with contrasted effects. In annual mean, a tendency to have more rainfall in cold regions, cold seasons, and a tendency to have less rainfall in regions with a Mediterranean climate, including South Africa, the Amazon region, Central America, or around the Mediterranean Sea. So you can access these informations in our interactive atlas. Play with themselves yourself. What is your variable of interest, your region, your time horizon? And you can access to these information in an interactive way. But what does it mean for extreme events? The upper panel is not mean temperature, it's the temperature of the hottest day. It increases more than the mean, disproportionately. Events that were very rare in the past are becoming more and more frequent. And that's a direct consequence of warming. And you can see the area where the increase is strongest is around the Mediterranean Sea. If we look at the last 20 years, the increase in hot extremes in Western Europe is even twice larger than in our models. Do we get it right? Do we correctly anticipate changes in atmospheric circulation patterns, blockings, that increase heat waves? These are open scientific questions. A warmer atmosphere includes an intensification of the water cycle and its variability. More very wet, very dry seasons, more very wet, very dry events. Looking at aridification processes, these appear in regions in the middle panel in orange. More warmings mean a decrease in soil moisture, proportional to the warming. It's the case for Western Europe in summer, the Mediterranean. It's the case for the Amazon, the Central Plains in the US, Central America. This is a major challenge for adaptation of ecosystem management and farming practices, as well as water use. If you look at the lowest panel, what you see that even in drying regions, you will have an increase in the record precipitation in the wettest day of the year. So you need to prepare both to increased water scarcity and increased excess rainfall concentrated in a few events. And this is a major challenge for multiple sectors on how to best prepare for that, avoiding maladaptation. I will give you a couple of examples. Adaptation that can be successful or maladaptation. Air conditioning. What do you think? If you are old, fragile, if you live in a dense urban center, in a poorly insulated flat, can be your solution. But you release the calories outside. You increase urban heat island effect. For those working outdoors, it can make it worse. Adaptation or maladaptation? Artificial snowmaking. Adaptation or maladaptation? You use public money to preserve an activity, jobs, economical activity in mid-latitude, mid-elevation mountains. But at the same time, you lock in investments into that direction, and then when it's not cold enough, you can't make it. So adaptation or maladaptation? Surface water storage. Can be an adaptation when you have issues with a very shallow underground water storage, so that you can store winter precipitation, use it in summer. But who pays for that? Who benefits from that? Does it affect ecosystem water use and in rivers and in water systems? Adaptation or maladaptation? And these are complex case studies that you will have to address in many situations. So I'll just go quickly through some of the main risks. And first risk of a warming climate is the loss of species and degradation of ecosystems. This is illustrated here from a modeling study of 30,000 of mammals, birds, reptiles, marine fish, krill, and even sea grasses and corals. And you can see that it's just using temperature and looking at organisms that would be exposed to potentially harmful conditions if they don't move, if they stay at the same place. You can see that the risk is already here now, in particular in the tropics for endemic species, coral reefs, and it will increase in space and severity with every increment of global warming. What can be done? Of course, protected areas, removing other pressures locally, corridors to support the movement of species, protection, restoration of ecosystems, that's critical. Limiting warming as well. And when you look at the severity of risks for different land systems or ocean systems, you can see that they increase with the level of warming for wildlife damages, permafrost degradation, loss of biodiversity or tree mortality. And they also increase with warming for multiple types of ocean ecosystems, starting from warm water corals, but even at the depths of the sea. No species is protected from the consequences of a warming climate. And in addition to our duty to preserve, protect ecosystems, their functions and benefits from their services, this shows hard limits for us. In a warmer world, when we lose the snow and the ice in the mountains, we lose the ability of the cryosphere to store water in winter and provide water in river systems when we mostly need it in summer for irrigation in particular. This will affect about 2 billion people, 2/3 of irrigated areas. Second example, slower growth of forests, yields decreased for crops. Which biomass will be available for us in a warmer world? And there will be hard limits. And today, the French energy and climate strategy does not manage to close for the use of biomass. And we need also to preserve ecosystems for biodiversity, not just use it for us. It's a major challenge, these hard limits. So higher warming, loss of response options for us, loss of opportunities. So in terms of tackling climate change, in terms of limiting risks, we need to limit the magnitude of warming. There are multiple risks for human health. I want to illustrate this one, the conditions of heat and humidity that can be harmful for human health. It means if you have a physical activity outdoors, you put your life at risk. It already occurs several days per year in tropical regions. And the number of years and the regions exposed will increase with every increment of warming. What does it mean? You remember the risks for building stadiums in Qatar or other places. It's already the case now. It's harmful for building sectors. It will be harmful for the agricultural sector as well. If you lose the ability to work outdoors, you can reduce the productivity and you will have economical losses, which is also a consequence of this threat. For some species, with the current practices, it is expected that the yields can increase with temperature and decline. One example is maize production that has a peak above 35 degrees and then a decline. So regions that appear here in purple are regions where crop yields for maize production without new adaptation approaches is expected to decrease. Will be more people to feed. Some of the food produced, some of the crops are for livestock feeding, some are for direct human feeding. If we keep the same diets, it will be extremely difficult to preserve food security in a warmer world with a larger population and threats for crop yields for core crop productions. You can see that for fisheries, the crop yields, the catch potential is projected to continue to decrease in the tropics. There's a large uncertainty for the Arctic and Antarctic, but we already see increased pressures from fisheries to move their exploitation areas in the Arctic, in the Antarctic, also threatening marine ecosystems due to increased potential capture pressures and potential sources of conflicts as well in these areas. I want to highlight the complexity of the risks. And they have been experienced already, for instance, in Pakistan and India, for spring conditions associated with extreme heat and drought. In this type of situations, the climate affects food yield, food production, food prices on local markets. But because people cannot work when it's so hot, they don't have any income. So you can see the two factors play in the same direction to threaten the ability to buy food that is needed at the daily scale. And when you look at the potential consequences, they affect malnutrition, and in particular, maternal malnutrition and child undernutrition. This is a major concern. I was on a call recently with UNICEF, extremely concerned about increased child undernutrition in many regions following extreme hot and dry conditions. When you look at, this is just one example, but when you look at adaptation strategies, public policies, they are often blind for vulnerabilities that are gender-specific or child-specific. So just pay attention to these dimensions. For instance, old women are extraordinarily more exposed to excess mortality due to heat waves. So analysis, public policies need to include these gender-specific aspects or age-specific aspects, and we're not there yet. I want to end by action. And when you look at heat-related morbidity and mortality, of course, the threat at the global scale depends on the level of global warming and extreme events that will intensify. But it also depends on the scale of adaptation implemented. And proactive adaptation can be access and quality of health systems. It can be also quality of housing and buildings, having urban design that creates cooling spaces so that people can have a rest during these extreme heat conditions. And you can see proactive adaptation, which has a cost, can limit the effect of a warming climate in some boundaries. Regarding food insecurity, the type of socioeconomic development plays a key role. And in a world where you have low population growth, you help people get out of extreme poverty. In a world where you have a reasonable income for small farmers, you protect farming land and you strengthen adaptive capacities of farmers, you can limit the magnitude of food insecurity risks. And this also calls for a shift in diets, less meat, more vegetable proteins as part of that process to limit pressure on land. In other cases, our own choices can increase the threats for a warmer world by local pressures on how we use land. There are irreversible aspects, including sea level rise. Sea level has risen by 20 centimeters since 1900. It will increase by 20 centimeters by 2050. By the end of the century, it depends first on us and the amount of greenhouse gases in the atmosphere, a factor of 2, 50 centimeters for very low emissions, possibly 1 meter with very high emissions. But it also depends on deep uncertainty. And we have deep uncertainty on some ice sheet processes that can cause their instability for sectors of Antarctica. What are the needs for large industrial complexes on coasts? Large cities growing on coasts. They don't want only the best confidence information. They want information on physically plausible high risks. So physically plausible high risks are if these unknown processes are triggered, what can be a worst-case scenario that is plausible? It is illustrated by the dashed line, up to 1.5 meters by the end of the century, and many more meters in the coming ones. And this is the type of information that is needed for risk-sensitive infrastructures that project on the long term. Sea level is a good example because responding to sea level rise requires long-term planning. And you can build on ecosystems, but if sea level rises fast, it doesn't work anymore. You can move sediments, sandbags, and gravel, and so on. Same thing, if sea level rises fast, you lose it. It was shown during last storms on the western French coast. You can build hard infrastructures like in Venice or London. It's very expensive. It will be only for wealthy, large cities. What about the rest? And the other options, they can be to stop building in exposed areas or to plan the relocation. This is a major challenge. We only see the first consequences: high tide, chronic flooding, extreme sea level rise during storms, erosion. It's only the beginning. It requires new skills and the ability to develop approaches within societies, deliberations, to develop how to do it, what is the will of the local communities to be done, so as to anticipate and implement the various responses possible. In some regions, risks are really high. In Africa, risks are extremely high for food production, preservation of ecosystems and biodiversity, health, and sea level rise. Already in Africa, climate change has reduced economical growth. It is the continent most affected. If we look at Europe, in Europe we have identified 4 main risks: extreme heat for people, for ecosystems, and for crop production, together with drought and flood risks. Water scarcity risks are important, and it's not just agricultural drought. It's also, the Rhine level so low, you block the industrial activity in the whole area, and it affects something like 1% of the German national growth. Same thing in North Italy, with the Po River, so low that it stops the economic activity at the very large scale. And large set of risks associated with flooding. We've built all our cities along rivers and on the coast, historically. So the amount of buildings exposed is very large, and it calls for anticipation, risk management, adaptation strategies to be implemented, and new skills, new jobs, new needs for climate services to be used in various sectors. I've mentioned small islands that concern French territories overseas, where there's a higher exposure to water stress because there's not a possibility to have large water storages underground, and a larger dependency on the health of ecosystems that play a key role in providing resources through tourism or local fisheries. And in some cases, there are issues of habitability, and I think, Wolfgang, you will address these issues together with solidarity challenges related to losses and damages. So maybe the take-home message for France, coming back to that, same thing, stripes, different scenarios, but for French temperature. The rectangle highlights what has been so far historical record warmth in 2022. If you look in the future, by 2050, if global warming reaches 2 degrees, which is likely given current policies, it means 3 degrees in France. It means the hottest year will be the mean year. So we need to prepare for the hottest year of 2050, 2040, 2030. The largest impacts were encountered with the heat wave of 2003. Some of you may remember that one. Large excess mortality, 2 weeks in August. In today's climate, this type of extreme atmospheric pattern would lead to 4 degrees warmer heat. So this is an example of information that is needed to prepare for worst-case things in every region, including in France. You can see that business as usual is not an option. And there will be calls for multiple transformations, adaptation, but also reducing emissions. Because if we don't reduce emissions globally and in every region, it will be very difficult to continue to adapt, and losses and damages will, of course, continue to ramp up. So let's look at France. We have reduced our raw emissions since the 1990s. It's the green curve. 2022, a decrease by 2.7%. Last year, first 9 months, 4.6%. Looks great, doesn't it? However, what are the effects of the energy crisis due to the war in Ukraine, inflation, and inability of people to just buy the usual consumption things? What is how to deconvolve the conjunctural factors from the efficiency of changes that affect the systems we depend on and help them transform? If these emissions are just due to being poorer, if the reduction is just due to being poorer, you can expect rebound effects, unless you really change the infrastructure, the practices, the norms, the social values that will lead to longer-term reductions. And if you look at the difference between raw and net emissions, you can see a challenge. Net emissions are after accounted for managed forest growth. And as I described previously, trees have excess mortality. The growth of forests has slowed, and you can see that the sink has reduced. When we account for that and for the fires in 2022, France might miss its second goal, its second carbon budget, after missing the first one and revising the second one downwards. It shows how hard it is to reach targets and how we need to not bet too much on ecosystems and their ability to store carbon. We also see that in the future, for France to keep with its own targets and those from the European Union, the rate of emission reductions should be increasing from around 2 to around 4-5% per year. It requires accelerated efforts in each sector, supported by just transition economical policies. And what do we see now in Europe? A backslash. The agricultural sector doesn't want to have an increase in the cost for fossil fuels used in the sector. The building sector has the same situation. So you can see that you need multiple skills to be able to design smart policies, building on the understanding of the disproportionate effects on some sectors and the engagement of all sectors so as to have a pace that can be supported and with benefits that can motivate to trigger further action. Just a note, the food system is 22% of the French carbon footprint, including half of it from imported emissions. One particularity in France is that you can see when we account for trade, we import a lot of emissions with the equipment and imports that we have. So we also depend on supply chains, and it illustrates why it matters that we tackle the climate footprint along these food supply or trade chains. The National Climate Change Committee had released a report on the French carbon footprint, showing the potential also for multiple industrial sectors to have a positive effect along the supply chain so that the regulations placed in Europe affect the production conditions in other regions of the world. So coming back to our remaining carbon budgets, you can translate every goal for future warming, like in the Paris Agreement, limiting warming well below 2 degrees or close to 1.5, in a remaining carbon budget. The one remaining for limiting warming at 1.5 is shrinking really fast. It's now estimated to be 250 billion tons of CO2, 6-7 years at today's emissions rates globally. What does it mean? It means if at the global scale, CO2 emissions stay at the same level, Before 2030, we have burned that, and therefore we are committed for a warming to exceed that level. It also shows that when we look at fossil fuel infrastructures, those planned and those already operating, if we keep them over the initially planned lifetime, we will exceed the budget associated with limiting warming well below 2 degrees. Translation: phasing out coal power plants earlier than planned, gas power plants earlier than planned. New investments in fossil fuel infrastructures, exploitation, production, is not consistent with the Paris Agreement. And that's not fully translated in shifts in investments out of the fossil fuel sector towards strategically solution-oriented sectors. So we can look at the pace that is needed. If we want to limit warming well below 2 degrees in green, we would need to decrease emissions by 27% by 2030, and to keep as close as possible to 1.5 by almost a factor of 2. It's a huge challenge, and it applies to CO2 as well as methane, the two main drivers of warming. What we also see, and that's the good news, there's a technical potential from solutions that are available now, well-known, public policies that have worked, to divide emissions by a factor of 2, playing on 3 main directions: technological innovation, practice, demand management, sufficiency, efficiency, and ecosystem-based responses. It's not one or the other one. If you don't use the whole package, it won't work. So in our reports, you can see an assessment of these options. I just want to start by showing where we are after COP28. In dark blue, you have implemented policies and what they imply: an increase in global emissions by 2030. In light blue, you have pledges from all countries. If all implemented, they could allow a tiny decrease, 2 to 5% of global emissions. In dark blue, on the right side of the arrow, you have the outcomes of the COP28 additional decision package, in particular for the energy sector. For the first time, at a meeting of parties of the UN Convention on Climate Change, phasing out fossil fuels has been discussed in a conference hosted by the president of the United Arab Emirates fossil fuel company. There's a description of what has to be done. It's not quantitative, they are not precise targets, but the main ingredients are there. And the most important pledge that was made was to triple the rate of deployment of renewable energy production and to double the rate of energy efficiency progress. If this is done, and it's feasible, if this is done at the global scale by 2030, we can save emissions of around 4 billion tons CO2, around 10% more. We're not there yet. It means we will not be on track if it is done only to limit warming at low levels. It would place us in a trajectory that would lead to around 2.5 degrees by the end of the century. But it's a non-negligible progress. There are sectors that have not been addressed, in particular the food system. It's really critical because it's a third of global greenhouse gas emissions. What can be done? This is the assessment in the IPCC report. It's not a roadmap. It's not what you have to do in a specific context. It's an assessment at the global scale, system by system. Energy, you have adaptation options for resilient systems, and then you have mitigation options. The bar size shows the potential. The color scale gives an indication of the costs. You can see the huge potential for renewable energy and the small one for carbon capture and storage, which is promoted by the fossil fuel industry and has been introduced in IPCC reports forced by fossil fuel-dependent countries to mention phasing out fossil fuels without abatement. Abatement means carbon capture and storage on the long term. But it's not taking up at the right pace, and the National Climate Change Committee has released a report last November trying to assess what is the true potential for France of using carbon capture and storage for very hard-to-abate sectors. It will have to be done. It will have to be focused on these hard-to-abate sectors. It needs research and development for it to be implementable, and it needs investments with large costs. In the land, water, food systems, you see a lot of various options, including efficiency, bioeconomy practices in a way, including the work with ecosystems and agroecological practices. It also highlights the importance of the demand side and shifts in diets, less animal protein supply, more plant-based protein supply. It's part of the solutions, it's affordable, it's feasible, and it can have health benefits. So in green, I have tried to highlight what can be the public health impacts of actual climate policies and effective policies. You can improve air quality, you can live longer in a better health with healthier diets, you can improve ecosystem health for soils, for forests, for agricultural and natural ecosystems. Looking at other systems such as cities, you can see that there are multiple challenges for adaptation and multiple building and transport sector mitigation responses. There's no single solution that fits all. Transport is the first emission sector in France, and in France, as in other places in the world, you have multiple responses: public transportations, active mobility, walking, cycling, which requires infrastructure, efficient vehicles, and electric vehicles. So it's a mix of these strategies that has to be designed, implemented, if you want to efficiently reduce emissions from transport. And again, you can have multiple benefits for thermal comfort, air quality, active mobilities, nature in cities, and improved health systems if it's well designed and well implemented. And looking at the industrial sector, on the short term, it's really the efficiency approaches, circular economy approaches that can be implemented now. Because there's a large need for research, development, for hard-to-abate sectors to develop the provision of substitutes to feedstocks, fossil fuel energy in these sectors. It's not available now, but it's the need now to develop these research and development processes so that these solutions will be affordable in 10, 20 years from now. And there are multiple solidarity dimensions that need to be designed, including, for instance, thinking of what could be a social security for adaptation to a warming climate. Maybe some of you have followed the news, those affected by the floods in northern France, displaced, no more income, struggling to find solutions, limited or covered by insurance companies. Expanding the social security system to adaptation could be part of a solidarity response, expanding climate change into the way we operate as a solidary society. I want to say a few things about what we call in French sobriété, sufficiency in English. It's often used to say you need to act in your own lifestyle, but in terms of IPCC assessments, it's really seen as strategies and infrastructures that can enable low-carbon lifestyles, make them affordable. It's the case for our research community practices. How can you transform them to reduce the carbon footprint of students, of academic research? In Europe, the carbon footprint of scientists is around 7 tons for their work per year, per person. For students, 2 tons. University buildings, food, heating, training sessions and the rest. It can be reduced, but you need to measure, you need to deliberate, you need to think of just transition practices. And there are multiple initiatives now that also try to develop new practices in research, in academic, to allow low-carbon professional lifestyles as well. And generally, the approach is in terms of what you avoid, and what you avoid and can have the largest impact is a long-term plane flight or driving a thermal car, how you can shift to a more sustainable transport or diets, and then what you can improve in terms, for instance, of building quality or heating practices. And of course, they have different requests in terms of investments, support. But this approach of avoid, shift, improve is quite critical for sufficiency strategies. And I don't want to dive into this figure, which is complex. It's just to say this is what you need to best develop. If you think of climate change, you think adaptation, reducing emissions, nature-based solutions as well. Each option, it has co-benefits and trade-offs. And you can look at these co-benefits and trade-offs using the lens of Sustainable Development Goals. Do you know what is the first Sustainable Development Goals from United Nations? Eradicating extreme poverty. That's the first thing. So when you think, for instance, of, I don't know, electric cars and extreme poverty, what's the link? Well, if cars are more expensive to buy, it can exacerbate the difficulty for mobility on a daily basis. If you make electric cars affordable, when you use them on a daily basis, they are cheaper. So thinking of, technological innovation, poverty helps think differently and think of making innovation affordable with the spirit of lifting people out of poverty in every region of the world. And you can see the same for all approaches. So when it's blue, it's when you have a synergy, a co-benefit. So climate policies can be health policies, can be poverty eradication policies, can be ecosystem, biodiversity preservation policies. And in orange, you have trade-offs. And so some of the most stringent trade-offs appear with land use. Increasing pressure on land for biomass, for multiple uses, can increase pressure on ecosystems and their preservation, can challenge food security in some regions of the world, or can challenge land rights, for instance, for small-scale farmers that don't have secure land rights in developing countries. Accounting for that is really critical to think of the profile of a response option, but also for scientists to assess what has been implemented, what can work, what can have trade-offs. If you increase the price of oil, it will have regressive social aspects, in particular for those who have old cars, inefficient heating systems, and low income. So including that in the design of public policies, in economical approaches, is critical. Otherwise, people will very well understand the unfairness of the implemented policies and can rebel, of course, against that. We saw that with the Yellow Vest movement. We see this now with the agricultural crisis, in particular due to very difficult income conditions for many people in the sector. So including these socio-economic dimension is critical if we want climate policies to be supported and to be successful. So basically, what we show is, if we don't limit global warming and act, it will be a major threat for a healthy planet and for public health. It can cause an increase in inequalities. We have a window of opportunity. We have solutions that can work, that need to be well implemented, but we need evidence to inform public policies, and we need advances in the knowledge basis to support transformations towards pathways that will allow us to be resilient in a warming climate, and pathways that bring us towards low-carbon economies as fast as possible. So what are specific needs for academic research and young professionals? The understanding of how to build with different forms of knowledge, local knowledge and academic knowledge, how to co-produce knowledge, how to strengthen the synergies between climate and other aspirations of societies, and how to inform and support behavioral change. Do you know what is the most stringent obstacle for effective climate action in Europe? In Europe, low perception of risk. It's linked to values, belief systems, lock-in from past choices. So engaging more broadly with society, allowing people to enhance their understanding of the causes, the consequences, but also the solutions is critical. Every moment of choice, every crisis can lock in towards high emissions, reaching adaptation limits, increasing climate risks, and ecosystem degradation. Is that the future you want, collectively? But every crisis, every opportunity of choice is also an opportunity to implement new options for lower emissions, systems transitions, shift in social, cultural values, norms, beliefs, lower climate risks, better equity and justice, and achievement of sustainable development goals. So I try to illustrate how much every increment of warming matters. You've seen that. The sense of urgency, because if we don't engage into these transformations now, it will be too slow, too late. The ability to act. So every choice matters, and I think your choices will matter as well. Thank you.
Thank you very much, Valérie, for this complete and global presentation, and beautiful presentation too, I have to say. I'm sure there's a lot of questions. We're running out of time, but it doesn't matter. We'll take the time to answer the questions. So maybe already you have questions in the... The first one is always hard to get. Okay?
Hello, thank you very much for the talk. You mentioned in your presentation that you will need both technological evolution and also ecological response to tackle the issue. The problem when you discuss with people about global warming, they form kind of two groups. They never agree. So do you have any opinion about that, or can we reconcile those two approaches? Thank you.
I think what matters is taking stock also of case studies, so as to show what can be achieved by one strategy, one option, but also the limits, what can be achieved by the other ones. It can be inspiring. Not everything is to be deployed at the same time, in the same way, in the same context. So in some cases, some options, urban centers or industrial activities, of course, there's a need for more technology-driven responses. But in other contexts, like agroecological response, they play a critical role for the resilience of, for instance, food production. It has been shown that climate-smart agriculture, for instance, has a potential, but also hard limits. And agroecological practices are most suited for deeper transformations and climate resilience on the longer term.
Thank you very much for this very informative talk. So I have a question about ocean currents. What is actually the current knowledge about the impact of climate change and increasing temperature on the ocean currents? We all heard recently about a possible collapse of the Gulf Stream current. So is it plausible, and what would be the consequence about that? Thank you very much.
Thank you for the question, because I've addressed the issue of potential tipping points and abrupt change, mostly hinting to instability of some Antarctic sectors. There are other possibilities for abrupt changes or tipping points in societies, in ecosystems, locally, but also in some aspects of the climate system, including what we call the Atlantic meridional overturning circulation. It's not the surface Gulf Stream, which is linked to the rotation of the Earth. It's really the 3D circulation patterns. And this circulation is driven by density gradients in the ocean. So it's sensitive to density changes with a warmer ocean or more inflow of fresh water in specific sectors of the ocean. So we know in the past that this circulation has changed abruptly. There's ample evidence from paleoclimatology, in particular during cold climates. Today, there are contrasted results from the monitoring systems or from reconstructions. There can have been a slowdown but it's still debated, in particular because a real measurement, with a system at depths in the Atlantic Ocean has only been implemented 20 years ago. So for 20 years, we see like a small drop and a recovery. And then looking at future climate, the issue is, do we have the right models? Are they adequate? So with very simple models, it's very easy to provoke an abrupt shift of this circulation and delayed recovery in some cases. With more complex models, it's more challenging. So the paper published last week in one of the Science or Nature journals is interesting because it's using one of the penultimate generation of climate models, not the latest ones. And then it does a systematic complex system analysis without adding greenhouse gases explicitly to freshwater inputs. It confirms the possibility with a sophisticated climate model to have an abrupt response to freshwater changes. It does not include the interplay between a warmer world and what would be a collapse of the circulation and the regional consequences. This has been already assessed with sensitivity studies in IPCC reports. And some of the major changes would be effects on the shifts in rain storm tracks and rain belts in the tropics that would radically affect water supply in tropical areas and Europe. And then from that study, what can we say? It does not show completely what would be like the warming levels that could lead to that. It still remains hard to determine. It shows it's plausible, but it does not show what would be the conditions under which it would develop. It also shows that there would be limited early warning signs. Because the question is, what can we monitor so that we could be able to detect maybe a few years before the start of the occurrence of such a shift, apart from the freshwater transport at the tip of South Africa. And therefore, it calls for a strengthening of the observing system in that region. So it's an illustration of a high-profile publication with a broad communication, sometimes poorly translated in plain language. So I remember because my neighbors told me, oh, it's too late. We've already altered the global ocean currents and Europe will be colder. No, we're not there yet. And it's a challenge in terms of allowing everyone to have a proper big picture of where we are now, what we know, what we don't know. But in my view, these risks of abrupt changes and irreversible ones are a strong motivation to act at scale now. We don't want to enter into that territory, of course. They would be very hard to manage. It's also instrumentalized now by some actors who want to promote very risky approaches, such as artificially altering solar radiation, geoengineering. And it is quite striking for me now that I see private interests using this knowledge and lacks of knowledge about tipping points to promote these types of dangerous responses.
Hi, thank you so much for your presentation. It was very interesting. And also as a French female student, I'm very inspired by you, so thank you so much. I have so many questions, but I'm only going to ask one. What do you think, do you truly believe that international cooperation can work? What do you think about this?
I think without international cooperation, it is not possible to have climate action at scale. However, the current process, UNFCCC and COPs, they are increasingly vested. One challenge, for instance, is the increased participation of lobbyists from various sectors, fossil fuel industry as well as agro-industry sector in the last COPs, without any strong system at play. So, in a way, a COP allows to capture the least common denominator of what all countries are ready for. It's always frustrating. But you can also have other alliances of those who are good-willing, who are implementing changes at a faster pace. And these types of alliances internationally can also be very inspiring to continue and keep momentum with the implementation of effective climate action. There's a strong tendency to insist on mitigation for international cooperation, and it's also key because at the moment there's a major need for investments in the Global South to support clean technology development. There's a potential, but there's a gap in terms of investment. So a lot of recent efforts from the World Bank and other institutions, development banks, have been to try collectively to move funding resources that are available, capital is there, towards where it can make a difference and make it available in those cases. So cooperation in that case is highly needed. The other example where cooperation is needed is related to adaptation. In different regions of the world, we face similar challenges, but we come from different perspectives, different approaches, and approaches that bring together, for instance, not just governments, but also cities from different contexts, sharing their experience. It is done between cities network, small cities, as well as megapoles like C40. It's quite impressive because it allows to increase the capacity and the knowledge basis of those who are hands-on, for instance, in the technical sectors of these cities, learning from the others and being able to not experiment and fail, but learn from what has worked elsewhere so as to implement in a more effective way. And international cooperation, it matters for scientists. It's crucial. It allows us to be better, emulation, learning from others. And I think it's also critical for students and being open to, the various challenges and perspectives from various regions of the world. It allows you to be a better human being. And understanding sometimes your privileges.